So Jocelyn, did we get it all sorted out? Jocelyn, can you hear me?
I can.
All right. I can tell you, I was at another event that I just left, and my internet crashed like 3 or 4 times in less than an hour.
Oh,
So I'm going to talk to Brian when he gets on to just be sure we have this backup plan.
okay.
It's been working all day, and I don't know why. But between 2 and 3, it was like, no way.
So who's recording? Do I have the capabilities of recording or?
So it has started now. We can pause it.
Mhm.
We'll just want to restart before the actual kickoff. So if you look at,
I see it up there.
yeah, so I'm gonna,
It says I can record on my computer. I have that capability.
It says we have 7 participants.
Mhm.
So only Brian and the panelists are likely to show up this early.
Well, you got Hubert, Daniel, Lucien, and some others.
Okay, but they know it starts at 3:30, right?
Mhm.
All right. Let me email Brian, because he was like, I'm on this morning. Rapid clip. And so we're going to wait just 2 or 3 minutes till the number kind of stabilizes, and then we'll get started. I'm sure others will join after that, but hopefully most people will be here by then. Phil, I know WSS generally starts about 5 minutes late. NASS always starts right on time. We'll compromise somewhere in there. Hubert raised his hand, Brian. Would you unmute him, please? So Hubert, did you want to say something?
Unintentional. Sorry.
All right. You're not the first.
All right.
That's all right.
Looking
All
for
right.
a great program.
Thank you. Well, the incoming count has tended to slow down, so we'll go ahead and get started and others may join. We have a few details to work through before we officially get started. I'm Linda Young from USDA's National Agricultural Statistics Service, and it's my pleasure to welcome you to the 29th Morris Hansen Lecture. As many of you are aware, this is the first time the lecture has been conducted virtually, allowing numerous people to join who may not have been able to do so otherwise. The Morris Hansen Lecture is jointly sponsored by WSStat, the Washington Statistical Society, and the USDA National Agricultural Statistics Service. This session is being recorded and will be posted on the Washington Statistical Society's website. We are thrilled to have several members of the Hansen family with us this afternoon. These include Morris's daughter, Evelyn Hansen Allen, his son, Morris, and wife, Marilyn Hansen, daughter-in-law, Margaret Hansen, two granddaughters, Heidi Harrison and Julie Hare, and a grandson and his wife, James and Monica Hansen. We certainly are glad to have the Morrison family continue to join us each session. So again, welcome to the 29th Morris Hansen Lecture. I now turn the program over to this year's chair, Brian Harris-Coteen. Brian?
Thank you very much, Linda. Good afternoon, or good morning, or good evening to all of you, depending on where you're joining us from. We have a very special panel for you this afternoon here in DC. Since we were unable to hold the lecture last year due to the pandemic, the award committee decided this year that we would have multiple speakers. And so we have a panel of three distinguished individuals, each giving a lecture here under the common theme of working with non-probability samples, assessing and remediating bias. So what we're going to do is have each one of them give their presentation, and then we'll have a discussion and question and answer at the end. You'll notice at the bottom of your screen, there's a Q&A button. You can add questions at any point in time while you're thinking of it to that, but we'll get to those at the end. So I'm going to move right ahead and kick it off with our first speaker here. Courtney Kennedy is the Director of Survey Research at the Pew Research Center. In this role, she serves as the Chief Survey Methodologist for the center, providing guidance to all of Pew Research Center's research areas. And her current research interests include data quality in online survey panels and approaches for weighting public opinion polls. Courtney's going to talk with us today about exploring the assumption that online opt-in respondents are answering in good faith. Courtney.
Thank you so much, Brian. Let's see, I'm going to try to share my screen here. And okay, Brian, can you confirm that the slides are up, please? All right, thank you. Well, good afternoon. It is an unbelievable honor to be participating in this event. To be involved in anything bearing Morris Hansen's name is just, it's really, it's very humbling. I never expected to be here, so thank you very much for this opportunity. On a bit of a lighter note, I hope that Brian and the other organizers have a sense of humor, because I have to say, when I heard about the theme for this year's talk, non-probability surveys, I did chuckle a little bit, right? Because Morris Hansen is kind of synonymous with probability-based surveys and design-based inference. And it got me thinking, like, so it's not necessarily the most natural pairing that you might think of. And it got me thinking of other, you know, maybe other unexpected or you know, unnatural pairings that you might have for a lecture. But no, I'm joking, of course. It's a perfectly good topic, and looking forward to this. Okay, so before I dig into some research, I want to just share with you 2 points. The first is that my perspective on this topic, non-probability surveys, is influenced very much by the sector that I work in, which is the public opinion polling. And I think that's important to mention because how non-probability surveys or opt-in surveys, I'm going to use those synonymously. I prefer opt-in for reasons I won't bore you with. But how non-probability surveys is playing out in the public opinion space is, I think, different in some ways from how it might be playing out in the federal survey space where I know many of you work. So for example, in opinion polling, non-prob dominates. At this point in time, so over 80% of US public opinion polls are done with just an online opt-in sample. And it's almost never the case that the non-prob is paired with a probability design in some way. No, instead it's almost always like just a non-prob sample and that's it. And so when I talk to you about, when I think about non-probability surveys, I have in mind just a standalone non-prob sample, which again, might be a little different from your concept. So I want to acknowledge that. Second thing is that I've been very blessed to work with a talented team of researchers on this topic over a number of years at Pew Research Center. In particular, I have to acknowledge Andrew Mercer, who's done a lot, if not most, of the intellectual heavy lifting on non-probability surveys for Pew. And I certainly hope in the not too distant future, Andrew gets this to be with you in this type of event as well. And Arnold Blau does a ton of the data crunching for us and is a wonderful analyst. So particular thanks to those guys. Okay, now to get started, I want to begin at a place where that I think is pretty well established, right? So there's been a lot of studies, benchmarking exercises, looking at the accuracy of probability-based samples versus non-probability. And the lion's share of that research shows that on average, probability sample estimates tend to be more accurate, right? I don't think that that's particularly controversial right now. More interesting to my mind is that there's been a number of research teams that have gone further and applied more sophisticated statistical techniques to non-probability data, right? Things like sample matching, propensity modeling, more elaborate raking protocols. And even in those studies, at least in my reading, even in those studies, if there's a benchmark involved, they still tend to see fairly large biases, even after extensive weighting. And so the question I really want to poke today is why? Why is that even after doing some extensive modeling, statistical adjustments, we still see fairly large errors in non-probability samples? Is it because we're just not smart enough, that our models are not sophisticated enough? Maybe there's some variable or two that would explain how the non-prob cases are different from the broader population. We just haven't identified it yet. Or is something different going on? Are perhaps some of these non-probability respondents not genuine and thus not immune to fixing with a model? Now, I want to be clear, we're far from the first team to point out that there's data quality issues in online opt-in samples. There's research showing that these days you can have some people from outside the US pose as Americans to qualify for US research. There's click farms, there's survey trolls, and there's kind of a raft of studies showing some online opt-in respondents tripping various data quality flags, right? So there's a decent literature that exists here. But so what I want to do is just kind of come right out, be explicit with what we're hoping to add to that conversation today. Things that we're seeing in our data that are maybe less well known, underappreciated, that we think are interesting, are going to advance this. So I'm just going to make these points now, and then going to show you the data, the evidence of why I think these are the case. So the first thing is bogus respondents in online samples. They are not randomly distributed across the sample. They are concentrated in certain subgroups. And in our work, those subgroups replicate sample to sample, panel to panel. It's a pretty reliable thing, as I'll show you. Second point is that for some subgroups, sizable shares of the non-probability cases might not actually belong to that subgroup. Again, I'll show you why I think so in a few minutes. And for this audience, I think it's important to keep in mind that our statistical models, they assume that respondent demographic information is reasonably accurate. But in some cases, I think that that's not true. And so for researchers who are doing, research like a hybrid design, and by that I mean you've got a probability sample and you've got a non-prob sample, and you're going to do production estimates with both. Whether that's a good idea, whether supplementing with non-prob cases is going to make your work more or less accurate, increase or decrease your mean squared error, our research is suggesting that that's going to depend on actually what subgroup you're looking at. Okay, so I want to sort of demonstrate this in the most recent large study that we've done on this topic. Andrew and colleagues are currently writing this up. We're going to put out a formal report in a few months, but I'm just going to give you kind of a preview of some of the things we're seeing that are interesting. All right, so last year we conducted 6 samples, all with online survey panels. 3 of the panels were non-probability opt-in panels, and then 3 of the panels were different probability-based panels that are recruited entirely or mostly with address-based sampling. So in my slides, ABS is a probability-based, address-based recruited panel. Opt-in is a non-probability panel. In each one, we conducted roughly 5,000 interviews with US adults. We administered a common questionnaire. It was loaded up intentionally with benchmark questions. And of course, with benchmark, I mean a question where we have a pretty accurate estimate from some high quality federal source. So we have reasonably good data on a ground truth. So things like what share of Americans have a driver's license, what share of Americans smoke, things like that, right? Okay, once we got the data back, we weighted each of the 6 samples independently so we was just raking, but it was raked pretty extensively on 12 different dimensions. That included core demographics, interactions of those like race by education, sex by age, things like that. We also adjusted on a number of dimensions where we know that online survey panels tend to have biases, things like volunteerism, things like civic engagement, frequency of using the internet, and so forth. Okay. So what we did, first of all, is compute the difference between the benchmark, what we think is the population parameter, and the weighted survey estimate. And I'm just going to kind of ease us into this. What I'm going to show you is something a lot of you have seen before, right? It's this finding that if you do this benchmarking exercise, on average, the opt-in data tend to have larger errors than the probability-based data, right? So here, what I'm plotting are differences from a benchmark, estimated errors. So longer bars are bad, that's more estimated error, shorter bars are good. Again, there's nothing new here. I just want to kind of ease us into this. And a formatting note, you can see here that in this study, the 3 opt-in panels performed pretty similar, and the 3 ABS panels performed quite similar. And in order to make my slides readable going forward, I'm just going to show you the average ABS result and the average opt-in result. Happy to provide the disaggregated results later, but the story doesn't change. Okay, so the thing that my colleagues and I are doing that's a little bit new, where it's at least much less often done, is to carry out this benchmarking exercise at the subgroup level. It's a lot more work to get all of those benchmarks for different subgroups and get all the weighted survey estimates. But we did that because we think that there's potentially some insights to be gained there. Okay, so I'm going to show you what that looks like. As a reference, I'm going to start with the results from the ABS panel. So what I'm showing you here is the average error in estimates for various subgroups based on the ABS panel data. And the main finding is these bars don't vary much, right? The error in the ABS panel data doesn't vary much from subgroup to subgroup, a little bit, but nothing dramatic. All right, now let's look at the opt-in data. With the online opt-in data, we see that some subgroups have really quite large errors, right? The estimates that are based on Hispanic adults and estimates based on young adults, on average, are off from the benchmarks by at least 10 percentage points. And I do want to acknowledge, though, at the bottom end of that scale, estimates for older Americans actually not bad. I have to say they're not too bad. But we do see these really, large errors in these two subgroups in particular. It's not limited to these groups, so I'm going to focus on these. Okay, so my question for you is, what should we attribute these large errors to? Is this some sort of non-response or non-coverage error, right? So these online opt-in respondents, they're responding in good faith. They're giving us good answers. They're just quirky. They're just unrepresentative in some way that we haven't modeled yet. Or are there a lot of bad faith, bogus respondents in these subgroups? And by that, I mean people who are giving us data that really is like unconnected to their actual attitudes and experiences. Or is the explanation some combination of the two? Reality's messy, right? I wouldn't be shocked if there's some combination going on here. But why does the mechanism matter? Why am I obsessing about this? Well, I think the important thing for this audience that I'd really point to is one of these things can in theory be fixed with models and one of them can't, right? If it's a non-response, non-coverage error, if we just find the right variables to explain the ways in which these guys are quirky, we can fix that, but we can't really fix the other. Okay, so how can we determine which mechanism is at play or is more important? I'll be the first to admit this is a really tough question. And might be fair to characterize the evidence that we've brought to bear to date to be more circumstantial than dispositive. So I just want to acknowledge that this is a really tough thing to address. But I'll tell you how I think about this, right? So if the mechanism is just like non-response or non-coverage, what I think we would see is that the responses we get from these folks, as a shorthand, like the Hispanic and the opt-in respondents, their data would be plausible. It would just be reflective of a biased sample. So for example, if the Hispanic non-probability sample had proportionally too many second and third generation adults and too few first generation, like that, we could see that they give plausible answers, but it just reflects that bias. On the other hand, if the mechanism is more, these are just bogus respondents to begin with, and these are garbage data, the answers would reflect that, they would reflect that they're not plausible and people are responding in bad faith. Okay, so to get at this issue of plausibility, we really have to pivot a little bit. So I'm not going to show you more deviations from benchmarks. So instead, what we're going to look at now are just the weighted survey point estimates for some of the benchmarks. As I said, we had 27 benchmarks. I don't have time to take you through all of them. I'm going to show you a few of the benchmarks that are particularly illustrative. So the first one is the share of adults receiving workers' compensation in 2020, right? So we have a benchmark. We know from the CPS that this is an incredibly rare characteristic. I believe that technically this is measured among workers, but it's very straightforward to recode both in the CPS data set and in the survey data set to recode it among all adults. So the base here is all adults, but regardless, this is a very rare thing. And what I want to, just emphasize is that it doesn't matter what subgroup you're looking at. This is a rare outcome. It's not literally zero, but it rounds to zero, right? Okay, so now let me bring in the online data from the ABS panels that's been weighted. So what do we see? There's some error here, right? These are a little bit too high. They're not perfect, but they're, arguably within reason. What do we see with the opt-in, the point estimates from the opt-in samples? Well, we see that almost a quarter of the young non-probability respondents in the Hispanic non-probability respondents tell us that they received workers' comp in 2020. And so, I think that my question is, what's the appropriate interpretation of these data? Is it, gosh, our young and Hispanic non-probability cases sure do get hurt at work all the time? Or is the proper interpretation, these data are not credible, and this is unlikely to be fixed with a model? All right, let's do another one. Share of adults with food allergy. We've got a beautiful benchmark from the NHIS. It's very clear this is about a 10% incidence thing. Again, this one does not vary much by subgroup, might be a smidge higher among Black adults, but it really doesn't vary much. With the probability-based data, again, not perfect. There's some error here. These are a little bit too high, but nothing crazy. With the opt-in data, we see that same pattern. We see these relatively high shares of reporting of food allergy among the non-probability cases for younger Hispanic. And honestly, what concerns me is that if you have a naive researcher look at these data, what they would conclude probably is that, gosh, there's a significant relationship here between age and having a food allergy and Hispanic ethnicity and having a food allergy. And that's completely bogus, right? That's not true at all, because we know that because we're grounding this analysis in the NHIS, but that's what the opt-in data would have us believe. And these opt-in data have been weighted pretty extensively. Another one is % of adults who've served in the military. This one's from the ACS. And here I'll point out there is a real life relationship between age and Hispanic ethnicity. So in real life, older Americans and non-Hispanic Americans are more likely to have served in the military. But again, we see this sort of distortion. We see this pattern with the online opt-in data. The online opt-in data would have us believe the opposite. It suggests that young people and Hispanics are the most likely to have served in the military. And again, that's bogus. It's not true at all. All right, so I want to demonstrate good faith that I'm not just going to cherry pick and show you results that are just make probability look good and non-prob look bad. So out of the 27 benchmark, I believe there were 2 in which the opt-in actually did a little bit better than the probability-based ABS panel data. And one of those is share of adults who have a retirement savings account. And this, I believe, is from the CPS as well. So what we see here is that, yeah, the ABS panel estimates are a little further off the benchmark than the opt-in. Now, I think this is a useful counterexample because, you know, as many of you have, I've studied survey non-response for a while. And to me, this does not mean that the ABS panel respondents are bogus. Rather, this to me makes sense in view of the large literature on survey non-response, right? We know that people who have higher socioeconomic status, more educated, more tied to their community, they are more likely to participate in surveys, definitely probability-based surveys. And retirement savings account is a sign of wealth, right? It's correlated with SCS and all that stuff. So to me, this doesn't mean that they're bogus. Instead, this is just makes sense based on the non-response literature. In the online panel, the ABS panel we have at Pew, we weight on education extensively to try to tamp down this bias. But what this result shows me is that our education weight is not fully correcting that, but it doesn't mean these guys are bogus in the probability samples. Okay, now I've been saying that we see some huge problems with Hispanic estimates, young adult estimates. I want to be perfectly clear. I do not literally think that Hispanic ethnicity or race in general is at all causal here. I do not think that any racial or ethnic group is more likely to give bogus data than another. Instead, what the data suggests to me is that this problem of bad respondents is more likely to damage Hispanic estimates. I don't literally think that some of these people giving us garbage data are in fact Hispanic. And I'll tell you why. I think there's 3 reasons why. The first thing I would emphasize is that Hispanic ethnicity is typically measured with a yes/no question. At least that's how we measure it at Pew. So it's measured with a yes/no question. Then you think about the fact that there's literature showing non-probability respondents are more likely to lie to qualify for more surveys. So maybe more likely to say yes to something like that. There's also a positivity bias with some, not all, but some non-probability respondents will say yes to whatever you ask them. And so, you know, the yes/no question, again, pick up on that. A third thing is you can imagine a sort of a different response style, right? You've got people responding very sloppily, like haphazardly, or if somebody's kind of responding at random, they're going to say hit yes 50% of the time to a yes no question just by chance. And so for all of these reasons, it's not shocking to me that we're seeing a lot of bad data in the Hispanic category. It looks to me like these are probably false positives. And again, my question to this audience is, can we really expect statistical modeling to fix this? I don't think so. All right, the last thing I want to share with you is a much more modest data collection we did recently. The goal here was to get at bogus responding just very directly, as opposed to kind of indirectly with benchmarks, to go directly at it. For this, we sampled 569 adults. This was yet a different online opt-in panel, a fourth one, not the first three that I showed you before. One of the questions we asked to try to get at bogus data was, are you licensed to operate a SSGN submarine? Which some of you might know is a nuclear submarine, right? So again, in a survey, the number of people saying yes, it might not literally be zero, but it would round to zero in a good survey, because this is just an unbelievably rare characteristic. But here's what we found. Overall, 5% of the opt-in cases said that they operate a nuclear submarine. And again, like crazy high share of Hispanic respondents and young adults saying that they operate a nuclear submarine. Just for good measure, we did another question asking about activities in the past week. 4 of them, unbelievably rare. If you said you did this last week, you're probably lying, or at least, you know, this would round to zero kind of thing. Again, it's the same pattern. We see this kind of bizarre reporting popped up with young adults and Hispanics. Okay, so what do I think are the main takeaways? For this audience in particular, I'd focus on the fact that our statistical models, especially for non-probability data, they assume that respondents are who they say they are, right? If there's a respondent who's a young Hispanic woman in Miami, we assume that that's true, and she's not in fact like a middle-aged white guy in Idaho. But what I'm seeing here is evidence, I would argue, invalidating that assumption for a sizable portion of young and/or Hispanic non-probability cases. And this leads to erroneous patterns concerning the effects of age and ethnicity. I was really struck by, you know, like that pattern with the food allergy thing, right? Those are bogus patterns that I think, you know, we should be aware of and concerned about. Again, want to be clear, I do not at all think that race or ethnicity is causal here. I think it's just kind of popping up in some of those categories for unrelated reasons. I would say, to be fair, that the non-probability data for older Americans looked pretty good. In the benchmarking exercises, those estimated errors were not bad. And we find very few bogus respondents reporting that they're in that older age group. So honestly, if a colleague came to me and said, I want to do a hybrid design and my target population is, you know, US adults age 65 and older, I don't think that's crazy. Like that's maybe not a terrible idea based on the data that we've had and have been looking at. And so, you know, I think the big point that I'd like to make is that whether, if we have a probability-based sample and we're thinking of supplementing with non-prob, whether that's going to help us or hurt us, it looks like it really might depend on which subgroup we're talking about. That's all I had to say. I look forward to your questions. Thank you.
Thank you very much, Courtney. I love the operating a nuclear submarine question. I think that should become a new standard question on all federal government surveys. We'll have to talk to OMB about doing that. Our second presenter is Yan Li, who is a professor in the Joint Program in Survey Methodology, JPSM, and as well as the Department of Epidemiology and Biostatistics at the University of Maryland, College Park. She serves on a number of advisory committees for various agencies, including National Center for Education Statistics, and has been a consultant with the National Center for Health Statistics and National Cancer Institute. Her current research interests focus on statistical method development for designing and analyzing complex samples and for health disparity analyses. And Jan is going to talk with us about her work on exchangeability assumption and propensity score-based adjustment methods for population mean estimation using non-probability samples. Jan.
Yes, thank you, Dr. Courtney. Yeah, let me share my screen. Yes, can you see my screen well? Okay, good. So let me enlarge it. Okay, great. Yeah, good afternoon, everyone. I'd like to thank you first, the committee, for your kind selection. And I feel so honored and humbled to be selected and give this talk. Yeah, today I'm going to talk about an ongoing work that is supported by NIH grant. And this work is extended from 2 papers. And yeah, the first author of this paper, Dr. Wang, is currently a postdoc fellow in the NIH. And Dr. Grobert and Dr. Keki are the 2 senior investigators in the same group as Dr. Wang in the biostatistics branch in DCEG National Cancer Institute. Okay, so as we know, non-probability samples emerge rapidly. These data are timely, however, can often subject to selection bias. Participants are often self-selected and volunteered to participate without pre-assigned selection probabilities, so which make population inference in great challenge. To reduce the selection bias, various model-based methods or the calibration methods or doubly robust methods has been greatly and widely studied. So among which PS-based methods caught a great attention recently. For example, the PS weighting methods estimates the participation rate for the non-probability sample units, and then take the inverse of the participation rate as the pseudo weights for the non-probability sample. In contrast, PS matching method, okay, so measure the similarity of the 2 sample in terms of the covariate distribution, and then they assign the survey weights to the non-probability sample units according to their covariate distribution similarity. Yeah, there's a multiple nice review paper that you can go into, published recently, and for the big picture in this area. Okay, so common, yes. So common assumptions for existing, say, PS-based methods include, like, they assume different types of propensity model, and also they assume like a conditional exchangeabilities, so which I will focus in this study. And they assume like a positivity, every population unit has a positive participation rate. And also they assume this probability sample is high quality, well representative of the final population, and so on. Okay, and model-based method have a different set of assumptions. They assume different outcome model and assume they are transportable from one population to another population. Yeah, so in this talk, I'm going to focus on this conditional exchangeability. Okay, first, a few notations. I try to keep notation simple. So first, the outcome variable of interest is Y. X is the vector of observed covariates. And I have U and C to denote the set of finite population units of size N. And C is the set of non-probability sample units, which belongs to the finite population. Yeah, So we observe the non-probability sample. However, we have the challenge here, which is not representing the final population. How can we make estimation then of the final population mean? We need this conditional exchangeability. So this conditional exchangeability basically states that conditional on this B of X, so which is a balancing score function of the covariates, okay, the Y would have the same mean in the two groups. One is a non-probability sample, the other is a finite population, okay. So in other words, that it requires that this non-probability sample would be representative of the finite population if they carry the same balancing score. Okay, so which requires that a basic criteria for the balancing score is this balancing score should be able to distinguish the non-probability sample units by their participation rates. A natural choice would be the participation rate, of course, okay? And the other choices of this balancing score, according to the Rosenbaum and Rubin, should be finer than, if not equal to, the participation rate. So the example they gave, the finest balancing score should be the X variable itself, the vector of the covariates, okay? Or the coarsest balancing score should be participation rate or its monotone function. A monotone function could be like a linear function, or could be the log transformed function or logit function. Okay, so as long as it's finer than or its monotone function of the participation rate, it can be served the balancing score that satisfy this assumption of exchangeability. Okay, so now a lot of research has been done to estimate this participation rate, which requires this reference survey. We use the S to denote it. Okay, so in addition to the reference survey sample data, we need a propensity model, and the various parametric or non-parametric models are assumed. And for example, if we assume a logistic regression model of the likelihood of being the units in the C versus the final population, where this G of X is a known function of the observed covariates, and the B is the unknown regression coefficient of interest. So we can estimate it by fitting this logistic regression to the combined non-probability sample with the weighted probability sample. Remember that one of the assumptions is that we assume that the weighted probability sample is well representative of the finite population. Okay, so with this beta hat sub W, we can define our balancing score to be either the estimated propensity score, or the estimated the participation rate, or its one-on-one function, such as monotone increasing log function. So here we use this linear predictor, okay, of this logistic regression to be the balancing score. And based on this balancing score, we will have this exchangeability holds. Okay, so with that balancing score, we can do a lot of things. And for example, we can use the PS weighting method to weight the units in the C by the inverse of the participation rates. Okay, or we can match the units in C and the probability sample, both samples, based on the balancing score. Okay. There's a lot of research and has been conducted in order to do these two methods. And nicely, they more often provided the theoretical proof to show that these two estimates are approximately unbiased. Okay, so however, there's one challenge. So when you estimate this model coefficient, and you tend to have this weights, right, weighted sample incorporated, and which make the variance inflated, especially when you have very differential weights in the sample, also in the sample weights in the non-probability sample, which is the common value, implicit common value of 1 versus the actual sample weights in the survey. Okay, so now the natural question is, can we estimate this model parameter by ignoring the survey weights, okay, in the logistical regression? So instead of using B hat sub W, we use the unweighted B to form our balancing score. Okay, so the question is do we still have the exchangeability holds if we conditional on the unweighted balancing score? Let us think. So as we know that this unweighted balancing score is producing the sample balance in the X, in the covariates, based on the C and S, based on the non-probability C and the probability S, probability sample S. Okay, and therefore the Y is therefore exchangeable. Its distribution is exchangeable between this C and S, conditional on the unweighted balancing score. However, what we want is not C and S are balanced. We want the C and U is the finite population. That Y distribution is exchangeable based on the balancing score. So we have a dilemma here, but there's one way, one thing we are lucky that we have already identified that B sub W hat, which is balancing the Y distribution in the non-probability sample versus the finite population. So the question is basically, is this balancing score based on the B non hat is a finer or the monotone function of that B hat sub W? So that's the question. For example, the linear monotone function could be B non hat equal to the constant times the B hat sub W. I'm sorry, I read this chat box. You may have. Am I okay? Can everyone hear me? Okay, good. Thank you. So equivalently, can we be that lucky? So for example, if you have a reference survey, probability survey, oversample the older group and the minority group, and then which requires you have a monotone function, so requires that your non-probability sample will also oversample the older group and the minority group and at the same proportional rate. So do we have that luck? So as we know that we have no control of the non-probability sample, right? So yeah, it's all by luck. I have to, yeah. Now we are thinking about how can we adjust this B hat now in order to make it a monotone function of the B hat sub W. Okay, so we propose this 3-step adaptive exchangeability assumption. So where the first step is still the same B non hat. Okay, so in this step, we are comparing the two X distribution in the two sample. One is from the non-probability, the other is from the non-weighted probability sample. Okay, so the second step, we produce another score, okay, which is the gamma hat sub W, to balance the X distribution in the S unweighted probability sample versus the weighted probability sample. Remember that weighted probability sample representing the finite population. Okay, so the purpose of this second step is to correct the bias in the B non hat, especially for those variables involved in the probability sample selection process. And the final step is add up these two balancing score, come up with our new balancing score. Okay, so good thing is that this B prime is still the function of the monotone function, which is a log function of this select participation rate. Therefore, conditional on this B prime, we will have that exchangeability holds, that Y has the same exchangeable distribution between the non-probability sample versus the finite population. Okay, so once we identify this B prime, we are able to conduct the PS matching method, for example, the kernel weighting method. So basically, you first use that balancing score to calculate the distance between the two units, one from the survey unit I, the other is non-probability unit J. Once you got that D sub ij, you calculate this kernel weight. Okay, so based on the kernel function, which can be standard normal, triangle. So and once you got these kernel weights, your final pseudo weights would be the sum of the sample weights weighted by this survey weights. So it's a smooth function of distribution of the survey weights to the non-probability sample. And finally, you can use Howard-Thompson type of mean estimation to get the to estimate the population mean. Okay. Okay, great. So these are the method section. For the simulation studies, we try to evaluate the new balancing score. We first generate the final population of 120,000 and 3 covariates following the standard normal distribution with the pairwise correlation, and are used to generate the binary outcome variable. Okay, so we vary the intercept so that they have a different prevalence, like 29, 15, and 7. They have similar patterns, so I only report 29%. And as you see that we have 2 outcome predictors, X1 and X2. For the probability sample and the non-probability sample selection, we use this PPS sampling with measure size is defined by this exponential function of X beta times a constant, which is A. The reason we have this A here, we set it to be the different values so that the survey weights, probability sample weights can be varied. CV of the weights can be varied. With the larger A, you tend to have a larger sampling weights. Okay, and also the selection variable for the probability sample is set to be X1 and X3. Only part of it, okay, selection variable overlap with the outcome variable here. And for the non-probability sample, because we don't know what's the underlying selection process, right? So we consider 3 possibilities. The first possibility, you can have this quota sample, like our example, like in my example, COVID data, later on I'm going to explain. They have large volunteer pool, but they cannot afford to get a blood sample from each of them, right? So they instead quota sampling from the big cohort using the joint distribution of selection, some variables, pre-selected variables in the finite population, which can be from the sensors or some external information. And then secondly, we consider quota sample on distribution only one of the predictors, not all of them. And then lastly, we consider, so we have no control, so volunteer samples with unbalanced distribution in both X and Y, X1 and X2. And we evaluate the 3 balancing scores using the relative bias, empirical variance, and MSE. Okay, so we expect that the weighted tend to be unbiased, but can have inflated variance. And the unweighted can be biased, but more efficient. And the new balancing score approximately unbiased with reduced variance. Okay, here are the results. We have 3 observations. The first observation, is kind of straightforward, because if your reference survey is self-weighted or close to self-weighted, so correction factor, right? So it tends to be 0. Therefore, it gives us the similar 3 estimates based on different balancing score. So the 3 balancing score perform similarly. And the second observation is on the scenario, you have variable weights of your probability sample, and you select your non-probability sample based on the joint distribution of X1, X2 in the final population. Okay, so in this scenario, you will have this 2 balancing score. One is unweighted, the other is the new balancing score, perform similarly. Both are more efficient than the weighted balancing score. So here is the results. So as you can see that this weighted balancing score and the proposed are both approximately unbiased. As the CV of weights increase, the new balancing score tend to be more efficient compared to the weighted balancing score. The same for the MSE. Okay, so next table, we have this quota sample based on a subset of predictors. So you are not be able to cover all the predictors of your outcome during the quota sampling process, only part of it. Okay, this scenario is more practical, right? And as you can see, the similar pattern, as the CV increase, CV of the probability sample, okay, increase, CV of the weights increase, and then your new balance score is getting more and more and more efficient compared to the weighted balancing score. Okay, and another different from previous design, you have this unbalanced unweighted balancing score is biased. Yeah, this is because they have the distorted X1 distribution in the B non-hat without adjustment, without the bias correction. Okay, and then lastly, I want to point out that the B non-hat, the unweighted weight balancing score, and the new balancing score tend to work together in terms of the variance. It's very close, very close, and in different settings of CV of the weights. Okay, so these are limited results from simulation, and now we apply this new balancing score to different data sets. I don't know how much time I have, but I only be able to cover one of them, I guess. So now let's look at the COVID data. Here we have this COVID survey, but using this BRFSS as the reference. So in this data example, we have the aim to estimate the proportion of US adults with COVID-19 antibodies from April 1st to the August 4th, 2020. And within the weeks of the study announcement, more than 460,000 volunteers responding. But obviously we cannot afford that many volunteers. So we select among this large volunteer pool using find the population distribution on 5 variables: age, race, sex, ethnicity, and the region. Okay, so as you can see, those 5 quota variables we try to use to do the quota sampling. Okay, as a result, a sample of only 8,000 subjects answered the questionnaire, provided the blood samples, and this quota sampling gave us a rapid data collection, but suffer from the selection bias. We use this BRFSS survey to do the adjustments. And this its CV of the weights is about 1.92 in our data. And it is a national representative probability survey, and it has a very large state level observations. And there, in addition to that 5 quota variables, they have this 11 variables related to seropositivity, which are not used in the quota sample. So this table shows compares the distribution of the COVID survey and the weighted BRFSS. As you can see, as expected, the 5 quota variables very close distribution. Okay, but for the 11 health-related variables, they are far off. And COVID data can be tend to be higher educated, homeowner, employed, and more healthier. As you can see, there's a selection bias, and we have to adjust it. Okay, here's the results. And as you can see that based on the weighted balancing score, it gives us 6.8% of undiagnosed seropositivity rate, which is higher than the other 2 balancing score estimates, and also with a much smaller standard error. Okay, so we are uncomfortable with this standard error, which is too big for the weighted balancing score. Therefore, we further doing the post-stratification of the KW weights. And then after post-stratification to the 6 quota variables, and the estimates go back to very close to the other 2. Okay, it seems the post-stratification saved the weighted balancing score, which tend to give a very large standard error. Okay, so this is the first example. And then the second example, I'm going to skip since I have maybe only 1 minute. But go ahead to do the conclusion and the discussion. Yeah, in this talk, I try to study this conditional exchangeability. So we have this weighted balancing score and the unweighted balancing score. Weighted tend to be variance tend to be inflated, but the unbalanced tend to be biased. We adjusted by 3 steps. First, identify the B naught hat. And then the most important second step to identify the bias correction factor by comparing the unweighted versus weighted sample. And finally, the new balancing score with this bias correction term tend to be the monotone function of the participation rate. Okay, so it will make the assumption hold. For the future area to study, as you can see in the example, that the post-stratification can bring the weighted estimates back to the same magnitude of these other 2 balancing score. So does that mean the balancing? Another way to create a balancing score is through this post-stratification. So does that also create this conditional exchangeability holds? And that would be very interesting if we can show that. And also, yeah, we need those variables, right? The 11 variables that we have to use to do the further correction. And then we need to carefully design our probability survey to collect those variables in order to make the further adjustments. And basically, the message we try to deliver that is the high quality, the reference survey is still required. We need that survey to be less variable, but informative weights. Okay, so the high quality probability samples are still in great demand, and especially when we use this exchangeability assumption, because we assume that the participation propensity is independent of the outcome given on all the measured covariates. So we need all the measure the covariables to make that assumption hold, which requires the high quality probability samples. Okay, so that's all I have. And thank you. Did I overuse the minutes?
You're just fine.
Thank you, Brad.
Right on. Thank you so much, Jan. Our last speaker is Jean-Francois Beaumont, who is the Senior Statistical Advisor at Statistics Canada, where he has been for more than 25 years. He's also the editor of Survey Methodology and the president of the Survey Methods section of the Statistical Society of Canada. And his current research focuses on statistical data integration, small area estimation, and other estimation issues with sample surveys. Jean-Francois, you want to turn on your camera and share your screen? There he is.
Thank you. I forgot to turn my camera. Well, thank you very much for the nice introduction. Good afternoon, everybody. And really thank you for this invitation. I'm really delighted to be here today, even if it's unfortunately not in person. And really honored to have been selected to be one of the speakers in the 3 speakers in this Morris Hansen lecture. And I've already enjoyed the first 2 talks, so I hope my talk will be half as good as the other 2. So in my talk, so now I will share my screen. I guess I need to do that. So in principle, you should see the slides. So in this talk, I will present 2 extensions of the inverse probability weighting method of Chen, Li, and Wu. And I will illustrate our methods using Stats Canada's crowdsourcing data. So this is joint work with a few colleagues at Stats Canada, Kevin Bossa, Andrew Brennan, Joanne Charlebois, and Kenneth Chu. Brief, well, at the beginning of 2020, at the beginning of the pandemic, Stats Canada advertised a series of online questionnaires on its website. And visitors to the website could fill in an online questionnaire on a voluntary basis on different topics. And we call this approach crowdsourcing. So a crowdsourcing sample is basically a non-probability sample of volunteers or online volunteers in that case. The first crowdsourcing sample contained over 200,000 participants, quite a lot. Subsequent ones were smaller, but range around the 30,000 to 40,000 participants. And really, these crowdsourcing experiments were the main motivation to conduct the research that I'm presenting today. So why use crowdsourcing? At the beginning of the pandemic, there was a strong desire to have timely and inexpensive information on the Canadian population. And it was thought that crowdsourcing would be a good way to achieve these 2 objectives. Obviously, we have to be careful of crowdsourcing. There are 2 main issues, participation bias or selection bias, and measurement errors, as Courtney mentioned in her talk. So in this presentation, I will focus on trying to address the participation bias. A brief overview of the presentation. I'll start by describing the data integration scenario that we considered. I will briefly discuss the inverse probability weighting method of Chen, Li, and Wu. Based on that method, we developed 2 extensions that account for the data structure and the probability sampling design, a variable selection procedure using a modified AKK information criterion, and a modified CART algorithm that we called NPP CART, NPP for non-probability probability. And then I will illustrate these methods using our crowdsourcing data. Suppose for now that we want to estimate a population total, theta, which is a sum over all units of a finite population, U, of a certain Y variable of interest Y. To estimate that population total, we have access to a non-probability sample. S and P, which is a subset of U. And in that non-probability sample, we observe a variable of interest Y, or there could be many variables of interest indeed. And we observe a vector of auxiliary variables X. We denote by delta K the participation indicator. So delta K is equal to 1 for participants, and delta K is equal to 0 for non-participants. In addition to the non-probability sample, we also observe a probability sample, SP, which is also a subset of U. And in that probability sample, we observe the same vector of auxiliary variables X, along with a survey weight WK. What is missing is the variable of interest and the participation indicator. So we don't have the variable of interest in the participation indicator in the probability sample, but we have the auxiliary variables. And as I said, in this presentation, and I assume that there are no measurement errors to simplify the discussion. So inverse probability weighting consists of modeling the participation probability, PK, which is the probability that delta K is equal to 1 given X, and we assume that that probability is strictly greater than 0. Another important assumption is that participation is not informative, which is related to exchangeability that was discussed earlier. Non-informative participation means that the probability of participating is independent of Y after conditioning on X. And this requires powerful auxiliary variables. So variables that are auxiliary variables that are related to both participation and the variable of interest. And this is a key assumption to reduce participation bias. Now, once we have a model, we can estimate the participation probability PK by P at K, and we can obtain a non-probability weight or a pseudo weight W at K and P, which is simply the inverse of the estimated participation probability. And then we can use that weight to estimate the population total as the sum over all non-probability sample unit of the pseudo weight times the Y variable of interest. Now, these weights can be calibrated to increase efficiency and to achieve double robustness, as you would do in the standard probability survey. But I'll focus in this talk on the estimation of the participation probability and inverse probability weighting. An alternative to modeling the participation probability is to model the variable of interest Y, as we do in statistical matching. The main practical issue of that is that often we have many variables of interest, we have many parameters that we want to estimate, and this means that we may have to validate many models. So that's the advantage of inverse probability weighting, is that there is always one model to validate the participation model. So at the expense of possibly increasing or having a less efficient estimate. How to estimate participation probability? Often a logistic model is postulated. So where the participation probability is a function of X, the auxiliary variables, and alpha, a vector of unknown model parameters. So we estimate alpha by alpha at, and we obtain the estimated participation probability. So the main question is how to estimate alpha. In an ideal world, we would use maximum likelihood estimation, and we would solve that estimating equation for alpha, and we would get the estimate of alpha and the estimate of the participation probability. But this approach requires the auxiliary variables to be available for the entire population. But if we have that, then the problem is really similar to waiting for survey non-response, and there is not really any issue for weighting. But the trouble is that we rarely have all the auxiliary variables for the entire population, and therefore we cannot use maximum likelihood estimation. So what was recently proposed by Chen-Li and Wu is to use a pseudo maximum likelihood method, where we replace the sum over the finite population by a sum over a probability sample, and we attach a survey weight to each unit of the probability sample. So basically, we are applying the Orbitz-Thompson estimate. That method applies the Orbitz-Thompson estimator to the estimating equation. And in this way, we obtain a non-biased estimating equation that requires knowing X for the non-probability sample and the probability sample, but not for the entire population. So simple and very clever idea. And an important special case of the logistic model is the homogeneous group model, where the participation probability is constant for all units in a given group. So the participation probability is equal to PJ for all population unit in group G. And if we use that model along with the Chen, Li, and Wu method, the estimated participation probability for a unit K in group G becomes simply the participation rate. So the number of people in group G in the non-probability sample divided by the estimated population size in group G estimated from the probability sample. So in practice, we never really use the output of a logistic regression. We always form homogeneous group based on these probabilities. And there are two main reasons for that. Using homogeneous group brings some robustness with respect to a misspecification of the logistic model, as shown in Aziza and Lesage. And it also avoids very small estimated probabilities that could cause instability in the resulting estimates. How to form homogeneous group? We consider two ways of forming a homogeneous group. In the first, we first compute probabilities from a logistic regression, and then we create groups that are homogeneous with respect to these estimated probabilities from a logistic model. So the standard approach for non-response. And the second approach that we consider is the use of classification trees. The choice of auxiliary variables, of relevant auxiliary variables in interaction is really important for logistic regression, or the choice of homogeneous group. This is key to reduce bias. So in practice, in our application, our auxiliary variables were often categorical, and crossing them all would not have been an option because this would have led to too many cells. So there is a need to choose variable interaction or homogeneous groups. There are standard procedures for that, but they cannot be used directly because the pool sample, the probability and non-probability sample, is not an IID sample. The pool sample uses a probability sample that might have been drawn from a complex probability sampling design that must be taken into account. And so that's why we developed two extension of the Chen, Li, and Wu method, a stepwise selection procedure using a modified AKK information criterion, and a modified CART algorithm, also based on a modified AKK information criterion and PP CART, that I'm going to discuss next. What is a modified AIC? First, the AIC is a likelihood-based criterion that is used to select a model. If we have a number of models that we want to choose one out of them, we typically compute the AIC for each of those models, and we choose the model that has the smallest value of the AIC. So the classical AIC, let's say just for logistic regression, is equal to -2 times the log likelihood plus 2 times Q, the number of parameters. So this classical AIC could be used if we could use maximum likelihood estimating equation, which in this case means that we could use the classical AIC if the probability sample is a census. But the probability samples that we have is far from being a census. So how can we address that? So we borrow from an idea from Lumley and Scott in 2015, who modified the classical AIC when pseudo maximum likelihood estimation is used to estimate model parameters from survey data. So our context is a bit different, but we can use this same idea and come up with a modified AIC that is really similar to what they proposed. So our modified AIC is equal to -2 times the pseudo-log likelihood. So we replace the log likelihood by the pseudo-log likelihood, plus 2 times the number of parameters. So the first two terms are really similar to the classical AIC. But then we need to add a third term, which is a penalty for using a probability sample instead of a census. And in our application, that penalty was not negligible. So there are two penalties: a penalty for the number of parameters and a penalty for using a probability sample. And we can use this modified AIC to select variables and auxiliary variables in interaction. Alternatively, we can consider CART, classification and regression trees, to create homogeneous groups. So CART implicitly and automatically select relevant auxiliary variables in interaction, but does not account for the data structure and the probability sampling design. So that's why we developed NPP CART. So both CART and NPP CART have two steps: a growing step and a pruning step. So the growing step of CART consists of recursively split the sample by minimizing an objective function, and we consider the entropy distance function, which is proportional to minus the log likelihood for the homogeneous group model. So with NPP CART, we take into account the sampling design by replacing the log likelihood by a pseudo log likelihood. So exactly as the same idea as in Chen, Li, and Wu. So very trivial. And then there is a pruning step, so we can grow a tree, a fully grown tree. And then there is a pruning step to improve stability. And that pruning step is consists of two sub-steps. The first is to determine a sequence of subtrees of decreasing size. And with both CART and NPP CART, this is the exact same procedure. So I won't discuss that in details. And then once we have a sequence of subtrees, we need to choose the best of those subtrees. So in CART, it is typically done using k-fold cross-validation. But in the context of that data integration scenario, data structure, it was not clear how to apply cross-validation and taking into account the probability sampling design. So we think there is some research that needs to be done. It was simpler to choose the subtree that minimizes the modified AIC for the homogeneous group model. And this way, NPP CART accounts for the probability sampling design in both steps. So we can use that algorithm to create a homogeneous group in two ways. The first one is the most standard way. So we take all the auxiliary variables, feed them into NPP CART, and then create a tree in an homogeneous group. Or we can start with a logistic regression to obtain estimated participation probability, and then use that single variable as an auxiliary variable that we feed into NPP CART to create the group, and we consider both approaches. Regarding variance estimation, we need to account for two sources of variability in variance estimation. And we need to account for the probability sampling design and the participation model. And to achieve that, we consider bootstrap procedures. We have two sets of bootstrap weights. The first set of bootstrap weights is used to account for the probability sampling design. And typically in practice at Stats Canada, we use the Rao, Wu, and Yu bootstrap. So that's what we did. And we need a second set of bootstrap weights for non-probability sample units, which is obtained by modeling the participation mechanism as Poisson sampling. And to simplify, we treat homogeneous groups as fixed, as is often done in the context of survey non-response. Now I can show some result of our empirical study. So we have a non-probability sample, which is a cross-sourcing sample that contains over 30,000 participants. So not small one, not very, very large. We have also, and the non-probability sample, of course, contains both Y and X. And we also have a probability sample, the labor force survey, which is a large probability sample containing close to 90,000 respondents and a response rate around 80% at the time of that experiment in the spring 2020. The probability sample contains only the auxiliary variable X. And in terms of auxiliary variable, we have 8: education, region, economic region, age group, sex, immigration status, employment status, marital status, and household size. The number of categories is in parentheses. And if we cross all these variables, these 8 variables, it leads to over 3 million cells. So clearly, there is a need to have some algorithm to reduce the number of groups. For that example, we're fortunate to have a reference survey for comparison. So by reference, this means a probability survey for which we have, which is independent of the LFS and crowdsourcing, and for which we have the variable of interest Y. And that survey is the CPSS, Canadian Perspective Survey Series, which is a probability sample, small one though, with only over 4,000 respondents and a response rate around 15%. We consider 6 methods. The first one is the naive method with only 1 group. So that's the basic, the most basic method you can think of. And then we consider 3 versions of the Chen, Li, and Wu method. The first one is the Chen, Li, and Wu method with all main effects, no selection. And we use Frank method of constructing homogeneous groups. So Frank, I won't detail, but it's a function of rank. So it's basically a refinement of the equal quantile methods. And we use 100 groups that were the number of groups was determined using the modified AIC. The second Chen, Li, and Wu method is now this time we use stepwise regression using the modified AIC with all main effect and single interactions. Again, using the simple Frank method of for constructing about 100 homogeneous group. The third Chen, Li, and Wu method is the same as the second, again stepwise with main effect and single interaction, but this time we use the estimated probabilities to create group using NPP card. This led to over 1,000 groups, so a lot more than in the previous methods. This might be either beneficial or harmful. It depends. It might help reduce the bias, or it might increase the variance as well. It really depends on the situation and the data. And then we consider true NPP card method. The first one is NPP card with no pruning at all, just we take the fully grown tree. It led to over 3,000 groups. And finally, the NPP card method with pruning with about 1,700 groups. Now I have some time to show a couple of results. Here is I show the proportion of people having a university degree using the different methods. So in red, we have the naive method, and the proportion of people having a university degree is over 60% with the naive method, and you can see the confidence interval as well. And then on the other side, the green bar, it's the CPSS estimate, so the reference, and we have about 30% of people with a university degree. So you can see that there's a big discrepancy between both data sources. And in that example, we see that all the methods were quite useful to reduce the bias. Maybe the main effect model was slightly inferior to the other one, but not by much. It's not surprising in this case because education is one of the auxiliary variable, and which is used to determine if someone has a university degree. So it's not surprising that we remove the bias in this case, but it's reassuring to see at least. So we've tested that on 9 variables. I won't show them all, but a typical result that we got is something like that, where there is a big difference between the naive estimate and the reference estimate, like in this scenario. And then the method reduce the bias to some extent, but do not remove entirely the bias. So that was a typical scenario. Sometimes we could almost reduce entirely the bias, sometimes not that much, but this is a standard scenario that we have seen there, and not much difference between the different methods. That's another thing that we've seen. We also wanted to see what happened if the naive estimate is not too far from the reference. So would the method introduce a bias that doesn't exist? And we were happy to see that in a couple of examples, that was not the case. So if you look at the confidence interval, and you'll see that none of the estimates are significantly different from the reference. So that was reassuring to see. Now we have a big probability sample, the labor force survey, close to 90,000 respondents. What happened if the probability sample is much smaller? So we did test that by replacing the LFS with the much smaller CPSS, Canadian Prospective Survey Series. And for the proportion of people having a university degree, this is what we've seen. So now you can see that there are some differences between the method. The 2NP Picard method seems to be quite good in removing the bias. The two-stepwise method, for some reason that we have to investigate, were not as good. The main effect model was not too bad in that case either. And for another more common variable, that we saw something quite similar. We still see differences when the probability sample is smaller. The NP Picard method are still good, but in that case, the bias is not entirely removed. So that's the most typical case. So in conclusion, I think I must be close to the end. So some conclusion of our experimentation. First, the variable education is by far the most important to explain participation in our experiments. It was the first variable to enter in our model and get the most important reduction of the AIC using education. A second conclusion is that with these data, the interaction were not that strong. So the main effect were quite useful in reducing the AIC, and the interaction did a little bit, but not that much. So in that experiment, all inverse probability weighting method performed similarly, especially when the probability sample was large, although we have seen some difference when the probability sample was smaller. But we expect to see more differences if we look at smaller domains instead of the national estimates. This is something that we will investigate in the coming weeks. And we could also see some different results with data set that would have a stronger interaction, which was not the case in those data. So in terms of future work, that one possible extension would be to look into random forests and see how they could extend it to that data integration scenario. So thank you very much. I think I can stop sharing.
Yes, thank you, Jean-Francois. I would ask the other presenters, Courtney and Jan, to turn on their cameras. And before we get started here on the kind of Q&A and discussion session, I did want to note, because some folks have been asking, Linda had noted at the beginning that the video for this lecture, as well as the presentation slides that folks have, will all be posted on the Washington Statistical Society website. So you can go there to, in the near future, to view this again, or to download their slides, or to point colleagues to that site if they weren't able to attend the lecture. I wanted to first give the panelists an opportunity, if they wanted to ask each other any questions, clarification questions or comments that you had. Do any of you have any questions for each other before we open it up to the audience?
I have an observation, Brian. First, I'd say it's a real pleasure to hear Jean-Francois and Jan's talks. I one takeaway I have is something I think is worth saying out loud is the research that I presented is in some ways kind of alarming, right? You're talking about a lot of error. My understanding of these talks is that the work that we're doing with these online non-probability panels in the US, I don't think it really generalizes, at least not very well, to the work that Jean-Francois and Jan are doing. Like, I understand that the non-probability samples they're working with, to me, sound kind of fundamentally different, where you've got this call for volunteers, you probably have a lot of like well-intentioned people just wanting to volunteer and help out. And I would not expect the errors that we see in these panels to necessarily be manifesting in the type of work that we're doing. So I think that's just one observation there. And it was really impressive, the advances that you guys talked about.
Thanks, Courtney. Any other questions or comments?
Yeah, I like to also share one observation. So among all different errors, including Dr. Kennedy mentioned in her talk, and I think what we observed is only part of it, or different types of error. And as also like Jean-Francois observed that even when we do different kinds of method to do the adjustments, and the bias is still there. So we cannot, by only using the methods, to reduce all the bias, and which may coming from the other types of errors that contributed from the measurement error and from, yeah, so like the error mentioned by Dr. Kennedy. And so I just want to share that the information we get is really need to be in good quality, which can be provided by the probability survey or data collection process. And it's not the method itself can do all the work. Yeah, that's.
Thank you.
Well, yeah. Well, I agree that actually I think that what you I agree with Jan, and I think that what you said in your presentation, Courtney, is also relevant for the data we have. It's just that we haven't checked whether it is it's difficult to check whether the data as or to evaluate the magnitude of bias that comes from the measurement error. So I would not go as far as saying that we don't have that issue in our with these data. And perhaps I have a small question for Jan. So you were looking at using the survey weights and different, and then you could get a huge increase in efficiency. So have you thought or tried to use the design information or the weight information as part of the auxiliary variable, along with an unweighted regression? Perhaps that you would have obtained some gains in this way as well. Some people are doing that from time to time.
Yeah, that's a good thought. We didn't try that, but that definitely could be one of the alternative methods to make comparison. But what in our the methods we propose in the second step, we just try to identify that variables that involved in the probability sample selection process, so that we can use that new score to do the bias correction function. But I bet this is actually the new idea. I would looking forward to try different methods to try that. Yeah, thank you for the suggestion.
So I want to encourage our audience members to continue putting questions into the Q&A. And I would ask my panel members here to start looking at that. There are a disproportionate percentage of questions for Courtney. So if you want to start scanning some of those, and I think some people put questions in the chat by mistake. So if you did that, if you would please put it in the Q&A so we all have it in one spot here. The questions towards the end there, I know there was at least one for Jan, and I think there are some for Jean-Francois. If you want to just take a moment there to scan towards the end. And Courtney, when you're, well.
Sure, I'll take, I guess I'll start with an easier one from Ellen Hertzmark. Thank you, Ellen. She asked a question about if one is reviewing an opt-in study, like a call for respondents on the web, one should at the very least require a loud statement in the weaknesses section. Also, all relationships between variables are suspect. Yeah, no, I think that's a good point. One thing that that I've tried to point out in US research, but this is probably, I think my colleagues and I in the polling sector are most guilty of this, is really not talking enough about this in our methodology section, which I think is Ellen's point. You know, it's kind of bizarre because the vendors in this space, right, the people who maintain and sell interviews with these non-probability panelists, they're very aware of the stuff that I presented, in the sense that they're aware that there's bad actors out there. They're doing all kinds of things to try to keep them out of samples. But what we find in our research is they're just not succeeding enough. Like, we can still find, you know, kind of alarming levels of them that slip through all the things that the panels have in place. And so it does seem like right now, unfortunately, there is a real burden on the researcher to put in place their own, you know, trap questions or data quality checks to try to weed out these cases. And I think the weakness of the field right now is the practitioners who use these types of samples rarely, if ever, it's hard to know if they're doing it. They almost never report on it. And so it's tough to know if researchers have really attended to this issue. So I would second your call for more attention to that. Maybe there's one for Jean-Francois or Jan?
Yeah, if Jan, did you find a question?
Yes, I found by time, like Erica asked at 4:34 p.m. How would one post-stratify if no benchmarking or related data exists at the same level? For instance, a national level estimate that does not have another related data source nationally. Yeah, so I guess this is the question for the post-stratify the COVID data after we get this PS pseudo-weights. And what we did is, yeah, using the benchmark from the census. So we from the recent census, we create that post-stratification cells for the 5 quota variables, and then use that as a benchmark to do the post-stratifying. So incredibly, that helped us reduce the variance a lot for those weighted estimates. So that is definitely a future study. Why it works so well? Does that also create a new like exchangeability assumption, balancing score? So that will be of very much interest for our future study.
Jean-Francois, have you?
Well, actually, most of the questions I think are for my colleagues, so I don't want to spend too much time. But I've seen one that is probably most likely related to my presentation. A question by Phil Cott, who asked why not solve a calibration equation rather than a maximum likelihood equation, which is a very good question. And indeed, it can be done, and I think it was already in the paper by Chen Li and Wu. I would presume that once you apply post-strata, once you make groups at the end, it doesn't matter much what you have used as an initial estimate of the participation probability, whether it's maximum likelihood or calibration equation. At the end of the day, we'll always use groups, and it probably doesn't matter too much, but that would be my intuition for that question.
And I see another one just came in for you, and we'll come back. We'll let you look at that, and we'll come back to you. Courtney, as you've been going through the many questions, we'll let you pick the ones that you think are the broadest interest or the easiest if you want to go that way.
Well, thanks, Brian. I think I can knock out a couple real quick. Fred Conrad, hi Fred, asked about the mode of data collection and whether that might be confounding. I apologize. This is an instance of me being like too close to the study to not emphasize that key point enough. So all the data that I presented was 100% collected online, right? And the difference was just which panel it came from and how was that panel recruited. And I realize now, thanks to your question, that my shorthand of ABS is confusing. And I apologize for that. When I said ABS, I meant a survey panel that's recruited with ABS, but the data collection is online. So it is the case that mode was held constant in among the newly collected data that I showed. If you bring in the benchmarks, right, then the mode varies. And so there could be a little bit of differences due to mode in the benchmark being different, but I would argue that not enough to explain the magnitude, right, of the errors that we saw. But that's that. Stacy Pancrantz asked if bogus responding was related to sort of the length of the survey, if maybe people were just getting tired. So we've not experimentally manipulated survey length in this line of research. That's a good idea. My sense is that that's not, that could play a role. I don't think it's a major driver because we do see the bogus responding in a couple of studies at this point. It starts from Q1. So I don't think that it gets triggered late when people get tired. I think the people that enter the process with not an intention to take it seriously or answer honestly are that way from the get-go. And then finally, Zenu Yu asked if we kicked out the non-probability respondents who are clearly providing bad data, do the non-probability samples do better? Good question. We've not run that yet. We will. Thank you for suggesting that. Based on what I know about the size of the errors and how many people would be classified as bogus, it would help the non-probability cases, right? It would definitely bring down the average estimated error. I do not at all expect that the non-prob would be then perform better than the probability. The daylight between the two would close from like 6 points on error versus 3 to maybe 5 points on error of average error versus 3. So I don't think it'd fundamentally change it, but they would definitely perform better. So thank you guys.
So I saw it, oops, now it moved on my thing. A question that was kind of looked like it was directed to both Jan and to Jean-Francois from Francois at 506, wanting to clarify, is it correct to say that the intersection of C and S needs to be large enough to apply the methods of Dr. Lee, but that is not necessary for Jean-Francois? You guys see that question? Do you want to respond to that?
Yeah, in my data set, I have pretty large, like a BRFS sample. So that is about 340,000. Yeah, that is pretty large. But for the COVID data itself, it's only like 8,000. And I think stability must be affected by the relative size from the survey versus non-probability sample. But I didn't see that I have to require that both survey to be big enough. And in my example, I have different combinations of sample sizes and affect the efficiency, but not, it still shows some good property of unbiasedness. Assume the model is correct. Yeah.
Jean-Francois, do you want to respond to that?
Well, I think that was really a question for Jan. and I think Jan has responded quite well to that. Or maybe take the question of Christian Boudreau, perhaps, if you mentioned that earlier. So Christian wrote, where the people in StatsCan crowdsourced state. I think the number of participants would have increased by much. No, the participants weren't paid. And also, is this a panel or where respondent asked to complete a single survey? This could be one important difference in the number of fraudulent respondents. So this was not a panel, but of course they were. So that was I think 8 different crowdsourcing. We call it experiment, but surveys if you want, maybe a bit more. There's an intersection between the participant in the different topic, because some like to respond to many, but it was not a panel per se.
Thank you. Courtney,
And I like to say one more thing, though. Phil Cutt is answering his own questions. Well, I like that. So he asked a question and he answered to his question, and indeed much better than I did the first time. So thank you, Phil, for answering your own question. So he said that you use the maximum likelihood in order to be able to use the AIC because it's a likelihood criterion. So I like that.
Yeah, we're glad Phil is answering his own question. Sometimes he argues with himself in public, and it gets very hard for anyone else to insert themselves there. Courtney, do you have another set of items you want to address?
Sure. We got a question from Jake Safranon.